Hey team, this is the last video in our first exploration of trees, and we are going to talk in this video about binary search trees, which is, we talked about how binary trees are the most common type of tree. Binary search trees are the most common type of binary trees. So this is a very, very common data structure that you would work with. A binary search tree, the basic definition of that is that elements in the left tree, the left subtree, so your left child is going to have a value that is less than the root. And elements in the right subtree are going to be greater than the value in the root. So we're talking about the data here. So if the data in so we have the data in the root and we have the data in each subtree. The data in the left subtree needs to be less than the data in the root. And the data in the right subtree needs to be greater than the data in the root. So if you want to search for an element in a binary search tree, then we follow this algorithm. If the tree is empty, then we return null. We weren't able to find the element at all. If a target equals the root node's data, so let's say we're looking for Harry, and we look at the root of our tree, and the data inside that tree is the word Harry, then we have found it, and we can just return the data that is in that node. If the target is less than the root node's data, let's say we had the, what's the Harry Potter name that's before Harry? We have, how am I not? Draco. Let's use the word Draco. So Draco comes before Harry. So if our root is Harry and we're looking for Draco, we know that Draco starts with a D that's less than H. So we need to look to the left of Harry. That means we are going to then visit Harry's left subtree. If the target is going to be greater than Harry. Let's say we are searching for Ron. When we see the hub, this, when we see the root of Harry, then we know Ron starts with an R that's greater than an H. So we need to visit the right subtree. So this is a recursive algorithm. If the tree is empty, return null. This is a base case. If the target is equal to what you're looking for, awesome. This is also a base case. Just return that data. Otherwise, we need to recurse on either the left subtree or the right subtree. We don't need to recurse on both because we know that the data we're looking for is either less than, which means it's going to go to the left, or it is going to be greater than, which means it's going to go to the right. So that is how we can search. Here's an example of a binary search tree. And here are all of the words from the house that Jack built. It's a nursery rhyme. So here you can see all of the words are in alphabetical order. So as we did in the last video, if we drew a line for each node, the word all, which is the first line, is the first word alphabetically in this nursery rhyme. So we have all. The next one is and. Then we have ate. Then we have built. So you can see how doing an in order traversal is going to give us all of these words in sorted order. These are all lowercase, so lexicographical ordering and alphabetical ordering will be the same. So Let's see. Um, let's say we are searching for the word mourn. So can we find mourn? So we start by looking at the root. The root is lay. Lay starts with an L. Mourn is greater than lay. So we know we need to traverse right. We're going to go right. Now we have the data called rat. Rat, it starts with an R. Mourn is less than rat. So we know we need to turn, we need to go left. We go left when our value that we're looking for is less than the data at a given node. So then we have milked, and MI is going to be less than our mourn. So mourn is greater than milked. So we need to go to the right subtree. We get priest. Mourn is less than priest. It will show up earlier in the list. So we need to go left. Less than means left. And we can check the data here. Mourn is the data at this node. So that's really convenient. It is present and we can return that data. Now, what if I will change colors to maybe green? What if we were looking for the word hammer? So we're looking for hammer. We start here at lay. Lay is our first word. Hammer is less than lay. So we go left. Then we have house. Hammer is less than house, so we go left again. Hammer is greater than cow, so we go right. Hammer is greater than dog, so we go right. Hammer is greater than forlorn, so we go right again. And hammer is less than horn, so we will go left. We have found an empty node. So we've hit our other base case. Remember, there is a base case for finding the node. So the node that you are currently visiting holds the data that you're searching for. And the other base case was that the node is empty or it's null. And that is what we reached here at when we were searching for hammer. So here we're returning null, and it goes back up here and back here and back here. This is a recursive algorithm, so you need to recurse not only your way down, but your way back. And what is returned is null. Whereas in the case of mourn, the value returned was mourn. Right now, we are finding values that we already have, which is interesting. So if we're looking for the word mourn, all it's returning to us is the same word that we were searching for. But perhaps these pieces of data that we're looking for are just identified by that word. There might be a lot of other information about the word. So the word lay, for example, might have all of its definitions. It might have a set of synonyms. There's more data about the word lay than just the word lay. So if we were searching through these dictionary definitions, we would search for lay and it would determine whether the data that is stored at that node in the tree, we would determine if that was identified by the word lay. But it is not necessary that the item that we are searching for is exactly or would be dot equals to what we're searching for. Sometimes it is that a field equals to. So let me try to make that a little bit clearer. Let's say we had a dictionary entry type, and inside that type, we have a string word, we have a string def, we have a string array of synonyms. So each of the nodes is going to have a dictionary entry. If we are just searching for a specific word, we are going to look in each data entry and we're looking at this field. So keep in mind what is stored at each of these nodes is usually a much more complex data structure than just a string. But we are representing the nodes as just the string for simplicity's sake in the drawing. It's usually the tree is going to hold a lot more helpful information than what you see here. Okay, as I have mentioned before, the in-order traversal of a binary search tree gives you the values in increasing order. So that means that the values are going to be returned to you in a sorted order. This can explain how a tree map, for example, we talked about a tree map, how a tree map can return its um, keys. It will return values in increasing order of the key. So we said that hash map, you can't rely at all on the order that values are going to be returned to you. But in a tree map, you can guarantee that order and you can guarantee that they will be in sorted order. The same with a tree set. You can guarantee that the items in the set are going to be returned in sorted order. That is because they are stored under the hood as trees, which is very helpful. Trees are pretty efficient if you are searching for an element. So if we're searching for an element, we only need to visit at most the height of the tree, which again is pretty convenient. The height of the tree in the best case is going to be log of the size of the tree, so of the number of nodes. That's pretty fast to search for things. Insertion is about that fast. Deletion is about that fast. So it is pretty convenient, assuming that your tree is fairly balanced. It is not guaranteed that your tree is going to look pretty and balanced this way. It is possible that you could create a tree if you're not careful. If you insert your data in reverse, or let's say your data is already sorted. So we already know what we're going to enter. So we start with all. And then we know that the next value we need to add is and. I'm going through these here. So we have all, we have and. The next one is going to be 8. Then we're going to go to built. If we have our data already sorted at the time that we are inserting values, we're just going to end up with a tree that just is one long linked list. So in that case, the log, like the log of the size of the tree, isn't really the same as the height of the tree. In a balanced tree, the shortest path to get something is going to be the height of the tree. The height of the tree is hopefully log of the size. If it is not insorted or it is not balanced, like this tree, the number of elements you would have to search for an element that's not in the tree is going to just be the size of the tree because the size is the same as the height. Not especially efficient. So well-formed trees, as what we call balanced trees, those are very efficient. If they're not balanced, they're about as efficient as a linked list because they are virtually linked lists. All right, with that, we have finished the last video. Go team. I look forward to talking about trees again soon. Bye, team.